Hello, everyone. First of all, thank you for the opportunity given us by this organization to present my studies. My name is Arzu, and I'm a master's student at Istanbul Technical University. Today, I'm going to present to you double-layer electrospun thermoplastic polyurethane gelatin nanofiber scaffolds for biomedical applications, and also effect of plasma treatment on adhesion of two layers. My supervisors are Professor Güner and Taygun. My presentation will start with small introduction about fundamental aspects of my work and then continue with objectives, followed by materials and methods, and finally reaches to the results and discussion parts. Bioactive dressing have recently seen considerable interest since they not only cover and protect lesions, but also improve wound healing process by stimulating the natural repairing process. The main goal of this nanofiber design is to mimic the original extracellular matrix until the host cells are able to grow and synthesize a new natural cellular matrix. Just to remind, schematic representation of wound healing process can be seen here, and this process is strongly influenced by the role of migration and proliferation of fibroblasts in the injury site. Fibroblasts will produce collagen that will link to the wound and also affect the process of revitalization that will close the wound. In general, all the cells need to attach to the extracellular matrix to grow and multiply. That's why it's important to produce an artificial structure which can replace the natural one until reproduction occurs. In this study, electrospinning technique was used, and this technique is preferred frequently for producing wound dressing materials. By this technique, we can get porous structure similar with at this picture we can see here. Since electrospun nanofiber mats have a high surface area to volume ratio and microporous structure, wound healing is started quickly by stimulating the fibroblast of the dermal layer. Fibroblasts, as I mentioned before, excretes collagen and growth factors for repairing the wound. On the other hand, when we talk about ideal wound dressing materials, firstly, it should be a mechanical barrier to environmental factors, but in addition to this, it should have good gas permeability, absorb exudate, and still prevent bacterial invasion. These properties are provided owing to the porous structure of the electrospun mats. With all of these properties, produced electrospun scaffolds have resemblance with natural extracellular matrix. In this study, double-layer thermoplastic polyurethane gelatin nanofiber scaffolds were produced for biomedical applications, and morphological properties were performed by using a scanning electron microscopy. And also, effect of plasma treatment on adhesion of two layers was investigated. The obtained samples with or without plasma treatment were compared by visually and based on water contact angle measurements. In the electrospinning setup, polymer solution was stuck in a syringe and placed on a syringe pump to control the flow rate. The syringe needle was connected to a power supply and electrically grounded plate used as a collector. When the electric voltage is given, electric field grows and it causes charges to be generated in the polymer solution. A single droplet comes to the tip of the needle, and normally it would have sphere form due to the surface tension. But electric field deforms this spherical form, and as we can see here, a conical shape form occurs, which is known as Taylor cone. When the electric field is increased further and overcomes the surface tension of a polymer solution, a jet of the solution is expelled from the tip of the Taylor cone and reaches to the collector. In this study, layer by layer structure was produced as two different polymer solutions were electrospun in a row. First polymer solution basically includes thermoplastic polyurethane and St. John's wort oil. For the first layer, this polymer solution was electrospun under preset conditions. Then, a second polymer solution, which includes gelatin and St. John's wort oil, electrospun above the first layer, as schematically represented here. Additionally, glutaraldehyde vapor was used as a cross-linking and stabilizing agent for gelatin. Just to make it more specific, the top layer includes 12% of thermoplastic polyurethane, which is TPU, and the bottom layer includes 20% of cold water fish gelatin. Oil was added in amounts equal to 30% of polymer's weight into both polymer solutions. Well, why did we use St. John's wort oil here? Because it promotes wound healing with its antifungal, anti-inflammatory, and antiviral properties. It stimulates collagen synthesis and allows transmission of fibroblasts to the wound. Remember, this was a very important step for the healing process. To summarize, double-layer electrospun scaffolds were produced in the study. The top layer, which includes thermoplastic polyurethane, TPU, is elastic, gives mechanical strength, and prevents the transition of water and other pathogens. The bottom layer occurs from cold water fish gelatin used as a collagen source and provides a moist environment. When we look at our natural scaffolds, we can see that all these properties are already provided by skin layers. Epidermis is a physical barrier, while dermis includes fibroblasts, collagen, and elastin molecules. It's clearly seen that electrospun scaffolds shows resemblance with epidermis and dermis layers of the skin. As I mentioned, layer by layer electrospun scaffolds were produced in this study. But since TPU is naturally hydrophobic and gelatin is hydrophilic, adhesion problems were seen between two layers. That's why plasma treatment was applied as a surface activation technique for the TPU electrospun mat. After the plasma treatment, gelatin was electrospun onto the TPU layer in 20 minutes. Let's continue with results and discussion part. For the electrospun scaffolds, morphological estimation was performed by using scanning electron microscopy, and as a result, homogeneous nanofiber structure was obtained in both layers. In the third picture, we can see the morphology of the double-layer electrospun fibers. Here we can see the contact angle measurements. First of all, contact angle measurement of electrospun TPU mat without plasma treatment shows 85 degrees. After the plasma treatment, its contact angle decreases to 42 degrees, and it shows us that it becomes more hydrophilic. However, after 20 minutes from plasma treatment, its contact angle measurement increases to 88 degrees, and again, it becomes more hydrophobic. Because of this, gelatin should be electrospun onto the TPU shortly after the plasma treatment. Lastly, the contact angle measurement of gelatin is 46 degrees. It proves that gelatin is hydrophilic compared to TPU. Without plasma treatment, we face some adhesion problems since TPU is hydrophobic and gelatin is hydrophilic. From these two pictures, separated layers can be seen clearly. For that reason, plasma treatment was used as a surface activation technique to provide better adhesion between the layers. And apparently, adhesion of two layers was achieved successfully with plasma treatment, as we can see at the last picture. To conclude, scanning electron microscopy results show that homogeneous nanofiber structure was obtained in both layers. The mean fiber diameter of the sample was 300 nanometer for gelatin layer and 1000 nanometer for TPU layer, which is suitable for a wound dressing material. With plasma treatment, electrospun TPU scaffolds was made more hydrophilic. By this way, better adhesion was achieved between electrospun TPU and gelatin layers. Overall results indicated that the obtained nanofiber mat can be a good candidate as a wound dressing material. Thank you for your attention.